So let's go over the handwritten exams first. Okay. Homework questions first. So handwritten problems are problem number 3. So we have 2 training examples in 2-dimensional input space, and there's no bias term. Then we can just write what is given in the problem as so this T denotes just a class of each training example. So first example belongs to the positive class. Second example belongs to negative class, okay? So from this x1 and x2, so the question here, we need to sketch out the problem in weight space, okay? So what is the weight space? Weight space is basically the space that is defined with weights, which is W1, weight 1, and weight 2, okay? And from this training example, we can just write, since omega tx is what is important, so omega is just omega WTX is W1, W2, and x here, the first training example, is 1, negative 2, okay? And this belongs to the positive class, right? Then this should be positive. And this gives us W1 minus 2, W2 is positive. Then let's look at the second training example. Second training example is 0, negative 1. If you do W1, W2, 0, negative 1, and we get negative W2. And this negative 32 has negative class, so negative, okay? So let's draw these 2 on this weight space. Then we can just write from the first equation. And from the first equation, since the omega 2 is smaller than W1 divided by 2. So we can just sketch here. And then the second things, this makes us to have W2 bigger than 0. So W2 should be bigger than 0. So we can just erase all this space. And we get this portion as our weight space, okay? Any questions? No? Okay. So the problem B is very arduous because you have to just repeat after the iterations. But unlike the hint set, there's a hint says that we have to update for 12 times, but as I did for myself, it ended up in 10 iterations. So I'm going to just start from the initial weights, 0, negative 2, okay? And the x, z, t. So where z is equal to omega tx, right? So first is 1, negative 2. So these 2 points stay same because they are just training examples. So we calculate for z and we get 4 here, okay? And with this omega tx, right, then we get 2 over here. And this class should be positive and this class should be negative. However, as you can see, the z here is positive. So this is failed, this is wrong. So we need to update the weight. W comma is W plus, in the question it says xt, I guess. So xt then gives us W plus 0, 1, which means W was 0, negative 2 here. So 0, negative 2 plus 0, 1. Okay? Then this gives us 0, negative 1. So our next weight is 0, negative 1. Okay? As you see, so omega tx, so just simple multiplication, 2, 1, okay? And this is class, positive class, negative class. But this class is predicted wrong, okay? Then we need to update the weight, is that omega plus xt, which means omega plus 0, 1. So our initial point was 0, negative 1. So our next point, weight point, is 0, 0. So let's start with 0, 0 from here. So when it is 0, 0, so you get x if you calculate for omega tx, then it goes 0, 0. However, in the questions we said that we need to update the weight whenever the omega tx, no, z and t is, zt is smaller or equal to 0, right? Equal. So since all the point z belongs to 0, so we need to update for this term and for the next training example. So we need to update for the two training examples, okay? Which gives us omega dash is omega plus, so xt, so xt is 1, negative 2, plus 0, 1, okay? And this gives us 1, negative 1, okay? So our next next point is 1, negative 1, and we have x, z, t. So omega tx gives us 3 and 1, okay? And 0, negative 1, this gives us 1. So again, this second training example has a wrong classification. So we need to update the weight for this, okay? So omega dash is omega plus 0, 1, okay? And this gives us 1, 0. So our next weight is 1, 0. X, Z, T. Omega tx gives us 1, and here we get 0, okay? But it should be 1 or negative 1, so we need to update the weight again for the second training example. Plus 0, 1. And this gives us 1, 1, okay? Next step is 1, 1. We need to repeat these like 10 times, so 1, negative 2. Then we get negative 1 here, and 1, 0, negative 1, negative 1. Okay. So as you can see here, now the second training example is correct, but the first training example is incorrect. So we need to update the weight for this training example. So which gives us W dash is equal to W plus 1, negative 2. And this gives us 2, negative 1, okay? So again, this is simple. Z is omega tx, so we can just have 4 here, and we can have 1 over here. Okay. So again, the second example is wrong. We need to update the weight by saying that this term. Okay. So our next point is 2, 0, and again. Now we have 2 over here, and we have 0. So again, the second point, second training example is wrong. So we need to update the weight like this. Our next point is 2, 1 and x. T. And from here, we have 0, but it should be 1. So positive, and this is 0, negative 1, and we get negative 1. So this is satisfied, but the first point, training example, is wrong. Okay, so omega dash is equal to omega plus 1, negative 2, so we get 3, negative 1. Okay, so 3, negative 1, again. What? Okay. Oh. Wait. Okay. So this first point, omega tx, gives us 5 here, and this is positive. And the second is 0, negative 1, and you get 1 here. So this is wrongly classified, so we need to update the weight. Omega dash is omega plus w plus 0, 1, okay? And this gives us our next point is 3, 0. Okay. Omega tx gives us 3, and this is positive, so correct. And 0, negative 1, this gives us 0, but it should be negative, incorrect. So we need to update weight with this, okay? So our new weight is 3, 1. So 1, negative 2 gives us 1 here. So this is positive, so correct. And 0, negative 1, this gives us negative 1. So this is negative, so correct. So our update for the weight is just over with 3, 1, okay? So let's go back to the 3a, so where we draw the weight space, okay? As I mentioned earlier, the weight space looks like this, and the weight space is here. So we need to we want a weight on this in this region. So the weight, the 3, 1 should be within this region. So let's figure it out. So 3, then 1, because this is like omega 2 is equal to omega 1 over 2. This should be 1.5. But we need is 1 here. So 3, 1 is indeed within the space, okay? So the problem says that we need to mark x on every point that we have searched in the algorithm. So this is just a simple. So we first go to negative 2, 0 and negative 1, 0, negative 1, and 0, 0. And then we move on to 1, negative 1, so here, and the 1, 0 here, and 1, 1, okay, so here maybe. No, here, okay. And then 2, negative 1, we go 2, 0, and we move to 2, 1, which is on the line. Okay, and then we go to 3, negative 1, and 3, 0, and then 3, 1, which lies within the space. Okay, so we need to find the point that lies within the space. So this point is first satisfied. Okay. Any questions regarding problem 3? No? Okay. So for the problem 3b, so I just go over all the algorithm and find the point. But you don't need to do that for your homework because the problem says that just mark X on the whatever points after you see the pattern. So when you see the pattern like these, like from here, you can just mark any points here, like you can just find the patterns. Okay, so you don't need to calculate all the 10 iterations for the algorithm. You can just calculate for 6 points and just predict the rest so that you can find the optimal point. So for the problem 10, so we have 1D data set for binary and linear classification. So as you draw, and this, as you can see in the problem, there's X here, and negative 1, 1, 3. And t is equal to 1, t is equal to 0, t is equal to 1. So this t is just basically the label, okay? So when x is equal to 1, the label should be 0. When x is equal to negative and 3, the label itself should be 1, okay? But as you can see in this graph, there's no way you can just classify these 3 points with a line, okay? So we need at least 2 lines, okay, in order to classify these 2 points, 2 classes correctly. So the problem 10a says like the data, argue briefly that this data set is not linearly separable. So you can just show this figure and says, hey, one line cannot separate these 2 classes. We need at least 2 lines to do that, and the 2 lines are not linear separation. This is like, it should be like non-linear, like this, okay, or something like that. So you can just say briefly about that. And for problem 10b, so assume that we have no bias term, and so that the parameters W1 and W2 are write down the constraints of W1 and W2 corresponding to each training example, right? So we define a Gx, and let's say Gx is omega Tx, okay? And the W is W1 and W2. And the x here is just training example. And in this question, it is given as phi 1x and phi 2x, okay? And this gives us omega 1 phi 1x plus omega 2 phi 2x. However, we know that phi 1x is given as x, and phi 2x is given as x squared. So this means omega 1x plus omega 2x squared. Okay? So what are the constraints? So constraint should be omega tx is bigger to 0, or equal maybe, when x is 1 and negative 1, when x is negative 1 and 3. So as you can see, when x is negative 1 and 3, the class of the level is like positive. It's t is equal to 1, so it's positive class, so we can write this, okay? So omega tx is negative when x is equal to 1, I guess, okay? So this constraint just is basically equal to gx, right? Here. And we know the equation for the gx, and we know that for x term, okay? So when x is equals to negative 1, omega tx should be positive, right? So you can just give x is equal to negative 1, and just plug into these x terms here. So we get minus negative 1 plus omega 2 should be positive, okay? Okay. And the second, when x is equal to 3, this should be also positive. So 3 omega 1 plus 9 omega 2 is also positive. And the second, the gx is negative when x is equal to 1. So omega 1 plus omega 2 is negative, okay? So we have three constraints, and let's define the feature space, features mean weight space, so that we can define a weight within that space, okay, with the constraints. So let's draw again omega 1, omega 2. From the first term here, so omega 2 should be bigger than omega 1, okay? So we draw a line which is omega 2 is equal to omega 1. And since omega 2 should be bigger than omega 1, you can just draw here, okay? And the second term gives us 9 over omega 2 is bigger than minus 3 over omega 1, which gives us omega 2 is bigger than negative 3 over 1 omega 1, okay? And this gives us a line like this. And since omega 2 is bigger than this omega 1 divided by negative 3, we can just mark this region. So we can just erase out these regions here, okay? And the next term, omega 1 plus omega 2 is negative, so omega 2 is smaller than negative omega 1, okay? So we draw line here, okay? And this should be smaller than this, which means we can erase all these regions here, okay? So our leftover regions are here. So that we find the weight space, so we can choose any point on this weight space, and any chosen point within this space will satisfy our conditions or successfully classify our functions, our training examples, okay? And I chose, if there's negative 3 here, and this should be 1, but this should be 3. So we can just choose negative 3, 2 as our weight, okay? So W1 is equal to negative 3, W2 is equal to 2. Now if we write Gx in terms of W1 and W2, we can just write Gx is equal to negative 3x plus 2x squared, and this is x over 2x minus 3. So as you can see here, so our function Gx goes through 0 and 1.5, okay? 0 here and 1.5. So our classifier is just doing this, okay? So for the answer here, so you can just write either the weights, negative 3,2, but you can also write for the points R1 and R2. Yeah, R1 and R2, so R1 is equal to 0, and R2 is equal to 1.5 for my instance. But if you have chosen another point in the weight space, like here or something like here, then you should have a different answer for the R2, okay? So R1 is equal to 0 because the weight space, the Gx is defined as this kind of equation. So this R1 is equal to 0 does not change, but R2 can change, depends on the any weight, any point that you have chosen on the weight space, okay? So is there any question for number 10? Okay. Let's go to the coding examples. Okay, so let's go over the coding problems. So for the problem 4-1, so 4-1 is basically feature extracting within the image. So this playing part is skipped, and then the second extracting feature part is important one. So for the first feature, we need to find the total average pixel located at the center of the image. So the center is defined as like that, okay? So we need to average it, so we need average for all the pixels within the image, center of the image, for all images that corresponds to the 0 image data and 1 image data, okay? And this is just simple using the NumPy function library so that we can do the averaging. And the second is total average, so we need to average the total pixel values. So we just use NumPy min for every data sets, okay? So that we can have features. Okay, this is very simple, so I'm going to skip. And then we need to build some feature vectors like this, okay? So phi is x is 1, feature 1, and feature 2. So we need to build the features like that, right? So the first x0 term here is NumPy h stack, which is horizontal stack of this NumPy 1s and feature 0, 1 and 0, 2. So this basically means that we have x0 and there's 1,000 ones here, and we have each feature 1 and feature 2 over here, right? And these feature 1s and feature 2s are defined as feature 01 and feature 02. So we get just horizontally stacked these three 1,000 points so that we can build a matrix or a data, okay? So this x1 is basically same, but these features are for the zeros, no, for ones, okay? And then we can just stack these two matrices into vertical stacking, okay? This vertical means we can just add one over here, okay, one, right? Yeah, one here, and feature ones here, feature twos here. So we can just build a total data set like this, okay? So this uses the horizontal stack and vertical stack defined in the NumPy library so that we can build a data set, okay? So now that we have built every features, so just printing is just simple, so I'm not going to cover this printing. And for 4-2, we need to classify the points that we just have produced with the perceptron. So this part is basically sine, as we created data. And the second term here is y here. Y is just giving the labels, okay? So for the first 1,000 data points, this was 0, and this is 1, okay? So we want to give label as ones for the zero digits and -1 for the 1 digits, okay? So giving the label is just basically equal to the problem 3, right? So problem 3, we had a training point of x1 and x2 and 1, -2, and there was t here, and t here was +1, So that it means that this is the positive class, and 0, -1 was -1, which means the negative class. Like these, we can just build labels y here. Y is a vertical stack of 1,000 ones, and the -1 for 1,000 after, okay? So that these data points are matching each other. Okay. And we initialize the weights with zeros, okay? For the problem 3b, I guess, we started from the point of omega is equal to 0, -2, right? But this time we start just zeros, okay? However, because we have like 3 data points, like some ones here, so this needs also weight omega 0, okay? So this time we have 3 weights, not 2, we have 3. But we're going to initialize them with zeros, okay? The next part is doing a perceptron. Perceptron iterations. So for problem 3b, we just solve by our hands for the perceptron iteration. But since we have like 2,000 points for this problem, we can just use our hands to find the weights, right? So from here, the CP here means the correct prediction. So we want to count the correct prediction made by the classifier, and so that we can find how many wrong classification it made, okay? So this is basically sine. So numpy append means if the numpy of a sine of omega tx, which is defined as x times w is equal to y, then we can sum the number of the correct prediction and append into CP. So for the CP and for the k times, 100 times, the CP will have some kind of value about the correct prediction made by the algorithm, okay? And this IDX over here is just making a random index so that we can fit the perceptron within that point of that index, okay? So with a chosen index, so y, let's say this is like 0 or 1, okay? So y1, 0, so y1 is 1 here, okay? But if omega weight times x over 1, so x over 1 of times w, or omega tx is not equals to this, okay? Then we can update our weight with this. This is basically the same idea that we used for problem number 3, okay? So any questions? So we just repeat this for 100 times so that we can fit our weights for the chosen 100 points. And then we repeat this kind of situation for 100 times so that we can see that our classifier or perceptron makes a way through the correct predictions. Okay? Any questions? No? Okay. So step 3, plot the results. So our decision boundary is given as omega 1x1 plus omega 2x2 plus omega 0. Equal to 0, okay? And then we can change this equation as omega 2x2 is equal to negative omega 1x1 negative omega 0. And then we can just write x2 is equal to negative omega 2 divided by omega 1x1 and negative omega 0 divided by omega 2. Okay. So now we have the equation for our perceptron classifier. Okay. So as you can see, the x1 are just given points, the bottom points. So you don't need to worry about these x1s when drawing a function. And for the x2, I find the x2 as like this, so we can just define x2p like that, okay? And if you draw the lines, then you will be able to see this kind of classifier, okay? Although some points are misclassified, but I guess these are very hard for perceptron or to classify correctly, okay? Maybe you need to expand the features into higher dimensions so that we can classify more correctly, but I guess the perceptron classifier just works fine for this problem, okay? Any questions? Okay, so basically problem 4-2, we just get the W's, the weights with the perceptron algorithm, and we plug in this our most optimal weight into this W2, W1, W0, so we can find that line, okay? So, so for the problem 4-3, this is also a digit classification with SVM. So for above question, we used perceptron to classify our digits, but now we're going to use the support vector machine to classify these two digits, okay? So our problem, the SVM can be equivalent to solving the following optimization problem, right? So the problem itself is very simple, okay? So the first part is just building your data, so I'm going to skip it. We're doing that over and over again, so I'm going to skip it. And for the optimization problem, we need to use the CVXPy, okay? For CVXPy, this W is the weight, okay? And U are the digits, ones or zeros, okay? And V is the another class. For if U is all the digits that are zeros, and V should be all the digits or data that corresponds to the digit 1, okay? And our objective function was given above here, like this, okay? But G here, we define G as 1, okay? G is just a constant term, so you don't have to worry about this G term. So we can just write objective functions like this. And our constraints was given like this, okay? Let's given like this, okay? So we can just write these 4 constraints within this CVXPy term, okay? With the defined objective and the constraints, we can solve the CVX problem, and we can get the W, the weights, with this CVXPy. So the rest of the plotting is also same with this equation, and we found the W0, W1, W2 with this SVM or optimization problem. So we can just plug in the values of W0, W1, and W2 in order to find a line looks like that, okay? So basically the SVM classifier and the perceptron classifier does his job on classifying these two digits. Okay? So this code is also same as 4-2, so I'm going to skip this. Next is multi-class classification with SVM. So we have done binary classification for now on, right? For classifying digits 0 from 1 or 1 from like 0, okay? However, now we're going to just classify multiple class with our SVM, okay? So this generation of data is given in the problem, so I'm going to not go over that. So the data points are looking like this, okay? And we need to classify these 3 groups, the first groups, and the second group and third group with our SVMs, right? So how are we going to do that? Is to use a multiple binary classification, okay? So this code is quite tricky because I defined some kind of function like mySVM. So mySVM is basically doing the SVM part, the optimization problem, solving the optimization problem that was given at problem 4-3. So first we gotta just make the datas like as we did before, and we define G as a constant, and W here is also weight, okay? And U is data points that corresponds to the x0, and V are the variables that corresponds to x1 of them, okay? And our objective and constraints are given as in the problem 4-3, so I'm not going to go over that. And you can just solve problem, and we can just find the weight values, okay? After we find the weight values, I'm going to draw a line on the feature space with these functions. So this function is basically the same, okay? So there's yp here. Yp corresponds to x2 in this question, previous question. So basically this bottom part of this code is for plotting. So we define mySVM. So this mySVM is just doing the SVM classification when data 0 and data 1 are given, okay? So when I give the data 0 and 1, this is, but we have multiple class, right? So class 1 over here, class 2 over here, class 3 over here, okay? But we need to give data 0 and 1, so 2 data for the SVM. So what I did was get a weight. So we can, from mySVM function, we can calculate the weight. So first, I'm gonna just find the classifier that classifies x1 and x2. So I want to find the SVM weights that classify this 1 and 2. Then the result of these might provide some weights that can make line of this, okay? So they classify 1 and 2. And the second part here is classifying 1 and 3. So 1 and 3. Then this also will be given like, I don't know, like this. If the SVM finds, SVM weights will be given like that. And for weights 2 and 3, mySVM will also give the weights that can classify these 2 points. So this can be looking like this also, okay? So now that we have 3 weights for 3 binary classification, we're going to use them, okay? Oh, you don't have to know these parts. This part is useless. And the bottom is the key. So class check is, so we get weights for all these 3 classifiers that classify 1 and 2, 2 and 3, and 1 and 3, okay? So we can say that our data is in the class 1 if the binary classification between 1 and 2 gives us 1, and binary classification between 1 and 3 gives us 1 as well, okay? So this is basically checking that, okay? So W1 and 2 is our weights that define the binary classification between 1 and 2. So if you multiply the data point on this W1 and 2, and it gives the positive, that means the first part gives us the positive of a class 1. And the second part is also same, but is now the classification between 1 and 3. But if this omega tx gives us positive, then the label should be corresponds to 1. And this, if 2 of this 1 and 1 satisfies, then we can say that this belongs to class 1. So we can just return label 1 if it belongs to class 1, okay? The second part is also the same. If the first binary classification between 1 and 2 gives us the label 2, and the second binary classification between 2 and 3 gives us label 2, then we can say that this point is class 2. So if this class 2 is true, then we can just return 2 over here. And for the third part, this is binary classification between 1 and 3. And if the classification between 1 and 3 gives us negative value, it means that our point corresponds to label 3. And the second part, if the binary classification between point 2 and 3 gives us a 3, then we can say that this point is corresponding to class 3 because it satisfies these both conditions. So if class 3, if the point is within the class 3, then we can say, hey, the point is class 3. So the else term here, although we know all points should be within 1, 2, and 3, but I add the else term so that we need. I want to define some kind of position that these perceptrons cannot classify. Okay, you will see what it means later. So this is like basically drawing scheme. So from x1 and x2, but x1 and x2 are some kind of just space, okay? Although the points might be important, but I just use all the points in this space so that I can classify the regions that corresponds to level 1 or corresponds to level 2 or 3, okay? So in order to check level, we use the class check that we define above, and we give this point x1 and x2. So if x1 and x2 was like point over here, then the label should be 3, okay? If label is given 3, then we can mark this pixel with green, okay? This pixel is green. And if we check for all the points in this space, then we will be able to find some space that corresponds to each class, okay? So this is just defining the color for each label, and this plotting term, I'm going to skip it, and then the result can be shown like this. So this painting is just classifying 1 and 2 when we find omega 1-2, okay? And then we find SVM between 1 and 3, and then we find the SVM between 2 and 3. With this information, we can get this outcome. So this is the reason why I check for every points on this space, so that we can just distinguish these points not with the line, but with the region, okay? If there's a new data comes like from here, so we can just safely say that, hey, this new point corresponds to class of 1, okay? So if for the homework, if you have just drawn 3 lines for this problem, it will be fine, okay? Any questions? Okay. Okay, I think it is all for today.